Continue on with waves. For most waves, the energy that they have is dependent upon their amplitude. And so the energy of a wave really depends in a relatively complex way toward the square of the amplitude, A. Now that's not the equation for the energy of a wave. Remember, we generally don't do much calculations based upon equations. We try to understand the basis behind them. We try to understand what this means more than actually do calculations in this beginning astronomy GE course. So if you go out to the ocean, what do you want to get hit by? A 2-foot wave or a 50-foot wave? Maybe you're on the big island of Hawaii and you go out there to surf and you get hit by a 50-foot wave. You better know what you're doing if you're surfing. If you don't know what you're doing, well, I guess the answer to that is called death, right? I'd rather get hit by the 2-foot wave. It just slightly pushes you a little bit. But a 50-foot wave, 25 times bigger than a 2-foot wave, not only pushes you, it can plant you. And so the energy's quite a bit different. In fact, just to give you a basics of this, if we have wave 1, and let's say that its amplitude is 2 meters, or 2 feet, excuse me. We'll just leave it without units right now since we're not really doing a calculation. So let's say it has an amplitude of 2. Then the energy of this wave, of this first wave, would be related to 2 squared or 4. Doesn't mean anything. What we're looking at is the relative difference of the energy for different size waves. If we have wave 2, like I just told you, where its amplitude is 50 feet, then the energy of this wave is related to 50 squared. Now that's equal using the idea that 50 squared is 25 times 2 squared. But I'll use the properties of exponents on a parentheses like that. That's equal to 25 squared times 2 squared. But remember, 2 squared is related to the energy of the first wave. So really the energy of this 50-foot wave compared to an energy of a 2-foot wave is 25 squared, which happens to be 625 times the energy of the first wave. Huge amount of energy for a 50-foot wave. So what that says is that if a 2-foot wave would push you a certain amount, a 50-foot wave will push you over 600 times harder than that 2-foot wave. So just to make sure you understand this, if I have a wave 1 that has a 2-foot amplitude, its energy is somehow related to that 2 squared. If I have a second wave with an amplitude of 50 feet, its energy is related to 50 squared. But 50 squared is just, in parentheses, 25 times 2, 50, the whole thing squared. And so what we say, is so much fun saying math to you, that this is distributed over the parentheses, that power. So it's going to be 25 squared times 2 foot squared. And 25 squared is 625, but 2 squared is related to that wave energy for a 2-foot wave. And so that's why it's so much more powerful. So the idea then is this: if light is a wave, then you could then say it must have an energy related to its amplitude. So what does amplitude have to do with light? What does it measure? And it turns out it measures brightness. So what that says is if light is a wave and behaves like a wave, as you would increase the brightness of a wave, you would expect then that the energy is actually greater for the light that's in there. And so this led to an issue that required Einstein to figure out from an experiment that no one understood the results, because again, you expect a certain behavior of light if it's a wave. In fact, is this explanation in one of his 1905 papers that gave Einstein his Nobel Prize. And this was him explaining the results of an experiment run well before this that no one could explain and did not understand. Yes, guys, more caffeine. Is called life at home, right? Living off caffeine. So I'm going to go ahead and erase this. All we're showing here is that if I look at the energy of a water wave, let's say when you're surfing, how does the energy change as the size of the wave changes? Because waves of water obeys the rules of waves for energy. That's related to the amplitude squared. But this is the problem that was facing scientists, where no one could understand it based upon the idea. By the way, this is light 3, excuse me. So this is going to be light 3 that we're talking here. So what was run is, this is called the photoelectric effect. So this has to do with light, and this has to do with electrical charge. Photoelectric effect. And this was the results of the experiment. They effectively had a piece of metal. By the way, I'm really giving a short, really simplified view of the experiment because we don't need to go into any great depth right now, other than to understand why this was a problem. And what did it lead Einstein to do in order to explain what was really happening here. And when he did this, it changed everything. So basically what happens is you shine light on this, and the light has energy. So the energy of this light does two things. It goes into breaking the bonds of electrical charges, and those electrical charges turn out to be electrons. It breaks their bond from the orbit of a metal sheet the light's been shown on. It breaks the bonds and they are emitted. So the first thing that energy goes to is basically breaking electrons from metal atoms. That sheet of metal that the light is shown onto has. But these also are moving with a certain speed and they have a certain mass, so they also have kinetic energy that they fly away from the atom. So the energy of the light goes into breaking the bonds of the electrons to the atoms, plus their kinetic energy of the electrons that fly free. And so this was the expectation. The bonds that the atoms have with their electrons is a given amount, doesn't change. So that means if we change the energy of the light, it won't change that, so it should change the kinetic energy. I'll say it again. So let's just explain this one more time to be thorough. We shine light onto a metal plate. Electrons are kicked free from the metal plate. To do that, that light has to break the bonds the electrons have with the metal, and then whatever remaining energy from the light goes into the kinetic energy of the electrons. If I change the amplitude of the light, that means the brightness of the light. If light follows ideas of energy for waves, then the kinetic energy should change. So that's what they did. So what they did basically was they changed the brightness of the light. And what they saw, instead of the kinetic energy changing, they just frankly saw more electrons kicked off, and they have the same kinetic energy. Now, let me see if I can actually write this better. So again, they changed the light brightness, same color and everything. They just changed the brightness. And so what they saw, instead of a change in the kinetic energy, they saw more electrons kicked off as it got brighter. Same kinetic energy. And if they made the light basically less bright, so what would happen? There was less electrons, but same kinetic energy. So brighter, more, dimmer, less. The whole problem here is the kinetic energy doesn't change, and they should if the energy of the light's related to the amplitude. But then there was another thing that complicated it even more. When they changed the color of the light, then the kinetic energy changed of the electrons. So that didn't make any sense at all, because color doesn't have to do with the amplitude, only the brightness. So this was the problem. So let me recap it one time, and then there's a few things to point out about color, and then we'll talk about what Einstein came up with. So what the issue here again, I'm going to say it one more time, you have a metal sheet. Doesn't matter particularly what metal types, it'll change a little bit. Mainly it'll just change this energy required to break the bonds of the electrons to the metal. But you shine this on, some of the energy of the light goes to breaking the bonds of the electrons to the atoms of the metal, and then the remaining energy goes into the electrons' kinetic energy that they have when they fly away. So they expected one thing. If they change the brightness of that light, it should change the energy of the light because brightness is related to the amplitude. But it didn't change the energy, it just changed how many electrons are being kicked off. And so if I made the light brighter, we had more electrons with the same kinetic energy. If I made the light dimmer, there was less electrons, but they all still have the same energy, kinetic energy flying away. 1/2 times the mass of the electron times the speed that they have. So that was strange. But if you change the color of the light shining on the metal, then the kinetic energy changed. But remember, the color of light is not related to the amplitude of the light, the brightness. So this goes completely against what you'd expect if light is actually a wave. But the contradiction is because light will basically bend around barriers and also add together, just like all waves, diffraction and interference. We know light's a wave. So we have a contradiction here. And contradiction says, ooh, there's something we don't understand. And so this was the state of where we were when Einstein started working on this. Now, a lot of discoveries led to him utilizing and leaping to a new understanding. In other words, a lot of new discoveries were being made at the end of the 1800s into the beginning of the 1900s. And the genius of Einstein was to take these other discoveries and bring it into the idea of light, of radiation. And so it was true genius on his part. And so let me do a slight aside about color. First off, we know from that little equation about light speed and frequency of light and wavelength of light that the speed of light equals the wavelength of light times the frequency. Go back and review what wavelength and frequency represents. Wavelength represents the size of a wave, one wave. Frequency represents how many waves pass by you every second. Because when we multiply them, we always have to get a big value, and there's a relationship. So now when we look at color, what really is the difference from one color to the other? When we see red, or if we see blue or violet or orange or green or any color, how do they differ from one another? And so the way that this works, it turns out that for blue light, it has a short wavelength. But if that's small, then that means the frequency has to be large. F is large, because when I take something small, I have to multiply by something big to get the speed of light. Now, if I look at red light, this has a large wavelength, which means the frequency must be small. And this is all in comparison of red and blue together. Blue light has a short wavelength compared to red light, but has a large frequency compared to red light. Whereas red light has a large wavelength relative to blue light, but a small frequency relative to blue light. And of course, if I do green or any of the colors in between from the rainbow of colors, it'd fall within those. Now, if I look and see that there's different shades of red or different shades of blue or green or anything else, they also vary in wavelength, but not very much compared to how those two colors vary. In other words, if I see different shades of red, there's a slight variation in the wavelengths of the red colors, but not a very big variation. And so what we find then is that color can either be described as a variation of wavelength or a variation of frequency. I mean, they mean the same thing because they're both related back together because of that equation right there. So that's kind of the status of things, of where it all was. You know, some people, well, first off, what we have are the eye-brain system, which is sensitive to those wavelengths or frequencies of color. And so the apparatus of the eye and the brain working together is how we discern color. And there's only certain wavelengths or frequencies that this eye system works. And there are some colors that we can't see, meaning it really doesn't have color, such as radio waves or X-rays or UV, infrared. These are the same thing as light, it's just within a range of wavelengths or frequencies, however you want to say it, that we're not sensitive to and therefore can't see. Okay? So this is what Einstein said and how he took care of this. What he said is that light is not only a wave, but it's also a particle. And that particle has a name. Particle of light is known as a photon. And it turns out that the energy of a photon, which means the energy of light, is equal to a constant called h times the frequency of light, where h is known as just a famous constant called Planck's constant. Well known and comes up with many different areas of physics in the physical world. So the greater the frequency, the greater the energy. So if I look at this, blue light has a much larger frequency than red light, so it has more energy. Violet has a larger frequency than blue light. When you go outside to protect yourself from burning, it's not for red light that you're trying to protect yourself. You're trying to protect yourself from the idea of ultraviolet, much higher frequency than blue light. And therefore it carries a lot more energy. And so the relationship of energy points out to something that is profound. And what that was is the idea wherein most of our history, if you're a wave, you're a wave. If you're a particle, you're a particle. But you're never both. Einstein showed for light that you can be both. And we call this idea that light can be a wave or a particle is wave particle duality of nature. A profound discovery that Einstein achieved. And when you apply this to that light being shown on a metal, it explains things extremely well. Because now what we have is this. Someone's horn's going out there. The idea is that when I shine light of a different color onto the metal plate, depending upon the frequency of light, that will give the energy of the light that's shining on this. So if I shine red light onto a metal plate, the electrons will be broke free, let's say, from the metal, but their kinetic energy will be quite small because the light energy is small because their frequency is small. If I shine a violet light or ultraviolet light onto the metal plate, the energy goes into breaking the electrons off, and the rest of that greater energy, because it's much higher frequency, goes into increasing the amount of the kinetic energy. So that explains that really well. So what about the intensity changing the number of electrons? Well, what that simply means is that the intensity is related to the number of photons coming from the light source. If I increase the light brightness, I'm increasing the number of photons. And therefore, there's more interactions of the photons with the metal and more electrons are kicked loose. If I decrease the brightness of the lamp, that means the amplitude is smaller. Then I'm decreasing the number of photons coming from the light source, and therefore there's less interaction of photons with electrons, and we see fewer electrons kicked loose. But the amount of energy of the photons, whether if there's a whole lot of them or a few of them, depending on how bright the lamp is, well, that's given by the color of light, and that won't be changed by how bright the lamp is or how dim it is, because the color is the color, given by the frequency or the wavelength, however you want to say it. And so go back and think about this a little bit. And so what's profound about this discovery and why Einstein won the Nobel Prize is that when he applied these ideas to the photoelectric effect, it explained everything exactly. And you could actually make predictions based upon that, and they made sense. And it was so profound because it changed our idea of what nature is like. And that's just an amazing discovery. That what before was separate phenomena of nature, particles or waves, not either. What he changed is that, particles and waves, and that they're the same thing of a like light, but different ways of representing it. The one last thing to say about this is it turns out that when you run wave-like experiments, you only see the wave nature of light. And so that's like diffraction or integration or Young's diffraction experiment. That's a wave experiment, so we only see the wave nature of light. Whereas if I run the photoelectric effect, that's a particle experiment, and I basically only see the particle nature of light. It behaves like little billiard balls striking the electrons. So those photons are like cue balls striking the electrons in a billiards table and knocking them free. And so there's this idea that there's no experiment that we can see both wave or particle nature, but they're fundamentally linked together and necessary to fully explain what light is. So light has a different way of acting than water waves, where water waves still depend upon with their energy on their size, as you all know. Now, turned out that one scientist said, well, hold it. If light can have a particle or wave characteristic in this wave-particle duality, what about stuff like us, particles? Can particles have a wave nature? And so he wrote several papers, and then they found an amazing agreement to his idea. His name was de Broglie. And he said that particles can have wave properties too. And so he actually won the Nobel Prize for this as a grad student. So what do you do in your career if you won the greatest prize just starting out? Well, he was a prince, probably had a lot of money, so I'm certain he was fine. He did work in science the rest of his life and became very famous because of suggesting this. And so it was not too soon after this that they ran some experiments and saw that particles had very similar properties as waves do. And so the essence of that was this. If, again, make that double slit experiment, here's a screen over here. And now, instead of projecting light on this, we throw electrons over here. And one thing was amazing. What happened was to see a whole lot of electrons behind the screen, then hardly any. Then a whole lot of electrons, then hardly any. A whole lot of electrons. And so it comes up with that diffraction pattern we saw for light, where waves interacted together, bent around the barrier, and interfered to cause the light and dark regions on a screen in Young's experiment. But these are where electrons show up. Notice this. If the electrons go straight in, there's no way they should be there, but they are there. And so people were really shocked and amazed by that. So the idea is, well, is this a real effect or not? So one thing they did is they performed the experiment so that there was only ever one electron traveling between the double slit over to the screen. And they didn't know where the electrons are going. They didn't know which slit it was actually passing through. So in other words, what they were afraid of is somehow electron passing through that slit was interacting with that one to cause this pattern. And so they made certain that there was only ever one electron passing from the double slit over to the screen. Yet we still got that pattern, meaning that somehow the electron was passing through both slits at the same time, even though it's a particle. How do you get a wave to, a ball to behave like two balls, yet there's always only one? It just says that the electrons are behaving somehow like a wave. Now, what's really amazing is what you would expect on this screen is this. So this is what we saw for where electrons are found. This is what you really would expect if electrons are just particles. Here's our screen right here. What we would expect is that the electrons will show up behind the screen there and behind the screen here, where the double slit is. Of course, they don't. They appear like a diffraction pattern, like Young's experiment. So I just showed you, except with one thing. If I put a little eye here to figure out where that electron's passing through, as soon as I look to see where the electrons are passing through, immediately we lose the wave nature of the particle, and they either show up there or there, but no other place. In other words, somehow the electron knows that we're looking at it, and then it behaves just like a particle. Now, of course, if I look at something, it means somehow I'm interacting with it. In other words, I'm using light or something to interact with it, and therefore it knows we're looking at it because we actually do look at it. And that affects the results of the experiment. Now, I'm not going to test you too much about this other than the fact, make sure that you understand that electrons behave just like a wave and behave just like a particle, as light behaves like a wave and also like a particle. Guys, just think about this. You have a wavelength and you have a frequency. Now, your frequency is so gigantic you don't see it. And the wavelength is so small that you can't discern the actual wavelength. I mean, it's minuscule, immeasurable to our eyes. So we don't see our wave nature. We see our particle nature. But we do have a wavelength and a frequency. Pretty astounding stuff. So let's go ahead and I'll stop this right now. We have just a few more things to talk about, and then I will proceed with beginning to talk about stars and their general nature. See you in a little bit.